then
Okay.
you set it up. You sound good.
I can do nothing about that up here. I'll just yell. So if you're new to the club, if you haven't been here before, you might consider joining us. Our primary output or primary purpose is public outreach, education of the public, and setting up outreach in the evenings at elementary school for science nights, hotels. A couple of times we're invited to wineries, and if you go out there with your telescope, they give us a free bottle of wine each, sometimes. So anyway, it's a fun experience. There's a lot of fun people in it. And tonight's show was absolutely excellent, very nice. So let me check my cheat sheet here. Okay, well, we're well into 2025 now, and we have the Tuesday night workshop, the Zoom workshop. We used to operate the workshop here on the campus of the museum, and we would teach people how to build mirrors or grind mirrors and build telescopes, and we'd fix telescopes for people after Christmas and they didn't know how to get the lens cap off, things like that. So we do that activity then, but after COVID, we switched it to a Zoom meeting, and now we have so many people out of the area that participate that we can't really switch it back. We've been cutting our attendance way down. So if you would like to join the workshop, telescope workshop, it's mostly talking now, but it's talking about problems that people have with their scopes, talking about science, recent events. And if you want to do that, you can talk to Tom Totten back there, and he'll tell you how to get the code for the Zoom meeting. It's Tuesday night from 7:30 to 9. We have about 6 or 7 regular people, and they're all very nice people. A lot of them are into photography, and they do excellent work. We also have a video log that runs on Monday morning from 11 o'clock to noon. It's on YouTube live. You can watch that. You can get that from our webmaster also about how to get on and watch that and actually ask questions that we will attempt to answer on the show. This coming Monday, one of the topics we're going to be discussing is the new asteroid they just found, 2024 Y64, I think it was. And it's a near-Earth object. It's going to come very close. It has about a 2% chance of hitting the Earth in about 2 years. So we'll be discussing that a little bit. I'm confident it's not going to hit us. I'm not selling my land. So tomorrow is our business meetings, which I think only the most determined people are interested in. But any member is allowed and encouraged to participate with it. We like the ideas. After the meeting, we have a star party here every second Saturday of the week, a month. And that's tomorrow for this month. So we'll be doing it with the weather clear, and I think it's going to be clear tomorrow night. So these things have become so successful with attracting several hundred people to each of these events. They're so successful that we've decided to extend our schedule and hold them even during pouring rain. Okay, so we're going to hear from several of our supporting staff. First up is Pat Partland, who is our merch manager and treasurer. And if she comes up smiling, we still have money.
Thank you, Jerry. Like he said, my name is Pat Partland, and I'm the merch coordinator and also the treasurer. So if you have your dues tonight, hint, 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 I will take your dues money. Just make sure your check is made out to the Museum of Natural History. And the merch part, I have one of our merch here. It's a tote bag that we have. It has a pocket in front and a zipper in the middle. And so it's pretty handy if you want to take it traveling or just want to put some extra stuff in it. For members, we have the membership directory. This hasn't been published for quite a while. Our last one was in 2012. It is only for members, so if you're interested in it, it is a whopping $1. So members can see Tessa Flanagan, the secretary, and she'll be saying a few words, or you can come and see me. Back to you, Jerry. Thank you.
Thank you, Pat. And now we're going to hear from our husband, Chami Amarasinghe, on the activities coming up for February. Don't risk it, you can walk.
That was my silly one.
Okay.
Thank you, Jerry. Okay, before I forget, I always forget if I leave it till the end. There's all kinds of propaganda here if you like paper, star maps, moon maps, webpage listings, and application forms for joining the club, and there's a bunch of museum propaganda there too, so feel free to graze if you like paper. So as far as outreach goes, we've had a couple of cloud outs that time of year. But coming up, of course, tomorrow night is the star party here at the museum, second Saturday of every month. It looks like we might be playing peekaboo with some clouds, but we can haul the moon and the planets through some fairly decent clouds, so we'll give it a shot. Then on Tuesday, we have a science night at Monte Vista School. I don't know if the rain will have reached us yet. And then on the 13th, on Thursday the 13th, we have a STEAM night at San Ynez Elementary. I think it's going to be pouring rain, so we're going to probably end up, I'll just go and do something indoors for them. Then hopefully it'll clear up, and on the 19th, we've rescheduled Cleveland School, which was scheduled for the 5th, but it got rained out, so we might luck out with that. And then third Friday of every month is Westmont with their public telescope night. And then on the 27th, we have Elwood School with their science night. So the details are up on our webpage somewhere. You'll be able to find them. And also for those of you who signed up for the Hollister Ranch event, we're thinking of rescheduling that on March 1st, but I haven't heard back from them, but I'll send you out an email as soon as I hear about that. And I also have, so for people who helped out at 6 or more outreaches last year, they get their membership extended for a year, and I've been handing out their pins from the Night Sky Network, little commemorative pins. I have a long list of names here of about 30 people who did that. I'm not going to read it and bore you to death, but I will, if I spot you, I will give you your pin. So, thank you.
Thank you, Chami. If you do want to do outreach with us, you have to be a volunteer at the museum. That involves a background check, and then you get a badge that you can go out and represent the museum. It's lots of fun. You don't really need a telescope for that. You just need an ability to talk to people in the night that you can't see about the stars. So next we have our secretary, Tessa Flanagan, who will make a few comments if she wants.
My comments were actually to encourage members to get the directory. So Pat did that for me. Thank you very much, Pat. I will go back there and have the members list. So if you want to come and get a directory, please do. We have about 116 members, so we're a good, strong club.
And now our events coordinator, Diane Welkenbach, if she would like to make any comments, if she wants. I don't see her. Okay, well, we'll get her next time. So now, here's our vice president. Here's Ronnie, who's going to introduce our speaker.
Captain Wilson, commander of the Starship, you do a good job. We're going to keep you. Thanks.
Would you
like to invite you, what he didn't say about our little Monday morning vlog is that we're coming up on year number 4 in March. And so he's the man that comes up with all the talking points. I transcribe them and run the program with about 5 or 6 other gentlemen who may or may not be in this room. I'd love to find out. Chuck, of course, you've already met. Raise your hand and keep it up. We have Tim Crawford. Are you here? He's probably on the screen. He's watching at home. Bruce, I heard in the planetarium. Here's Bruce. Bruce Murdoch, who runs the Santa Barbara Theater Organ Society, but has more fun here. And who else? Who am I forgetting?
Jerry.
Oh, well, Jerry's the president, and I'm the MC, and I'm the guy that doesn't know anything. I'm like the kid in Saturday morning, Dr. Wizard's Funhouse back in the 50s. You remember that? Gosh, Mr. Wizard, is that what happens when you pour this in here? My God. Anyway, listen, I was just noting a couple things when I got here tonight. Chad the Whale is now red, which is kind of interesting, a red light. Did you see that? Are you? Whittemore, is he here? Well, then he doesn't deserve to be mentioned. He's probably watching. Tom Whittemore is our former Westmont science instructor who knows all, tells all, and makes a damn good loaf of bread. I mean, I'm waiting for my sourdough for Christmas already. It's February. I'm going to ring up Chami in a minute. It is Friday, February 7th, everybody. Got to get my glasses. And I'm calling this a magic mountain ride. A mile down in the earth, we'll call it Deep Shaft Black Hills. And it's a little like going on Space Mountain in Disneyland because if they got it to work, I saw this program last September downtown, one of those second Thursday of the month, LCO, Astronomy on Taps. And I was very impressed by the young man, Chami Amarasinghe, who was here with his lady friend Bella, and may or may not have his parents watching us around the world. His mom is in Michigan, his dad is in Sri Lanka. I told him they might be pictured on the screen, but I guess we never know how many people are watching this. In any event, it's the underground search for dark matter we'll be talking about. What I like to do before we start the show is get my normal show of hands. We want to know who's here. If you're new, first time, even if you're one of Chami's guests, raise your hand. We want to know who you are. Oh, look at this. All right, well, you guys are special. Now, the ones that are members and longtime members, raise your hands. Look at that, what a mixed group. Now, you guys are going to work on the first show of hands and get them to sign up. It's only $20 a point. It's about the price of a meal in Santa Barbara these days. Let me make sure Jerry's doing his notes and I've got mine. And I want to tell Chami, make sure you stay here. So you're a handsome young man too, postdoc. Future science speakers, let me tell you who's coming. Exactly 4 weeks from tonight, March 7th. This is actually one of the museum's guests. He's going to be here to do all kinds of stuff, and you might want to see what he's doing for the museum. He's going to have a symposium or a seminar, some research on global warming. For us, his talk on the night of Friday, March 7th, right here in Fleischmann, Beyond UFOs, which are actually UAPs, they're called today by the Pentagon. Unauthorized anomalous, what's the P, phenomenon? April 4th, first Friday of the month after that, the return of UCSB postdoc and LCO intern Joseph Farah. You saw that astronomy piece about the supermassive black hole in the planetarium earlier. It's really kind of oranges. They've got pictures of it taken by radio telescopes. And this young man from UCSB, postdoctor Joseph Farah, who overflowed Farron Hall several years ago down below next to the planetarium, he will be back to do an update. He was involved in taking that picture of our supermassive black hole. So it should be interesting. May 2nd, we got a call-in to Night Sky Network, of which we're a member. Always send out great NASA astronomers and JPL scientists. I want to thank Chuck for the connection. I had no idea they're the people behind my little pin I got tonight. June, we have a picnic, our potluck. We meet somewhere, I think down here, where did we meet? Across the creek. So put down what would it be, June 6th? I'm not sure, whatever the first Friday. And then on the 11th, not July 4th, but the 11th, we're not going to be here while everybody's setting off fireworks around. So we move it a week beyond to the 11th, and Jerry's godson, Dr. Martin Cakin, who flew NASA's Ingenuity, little helicopter that went with Perseverance to Mars. He's the guy that actually ran that. And he finally got around. He's looking forward to coming to town, probably staying with the Wilsons, him and his lovely wife, Pat Forgy. And that'll be on the 11th. August 1st, Stephen Kane, Dr. Kane from UC Riverside will take us to Venus. He's an expert on that. And believe it or not, I may have December's in-house speakers taken care of. I know there's a gentleman who's not here, but his name is David Goldman. What is his last name? I can never remember his name. Do you remember it, Mike? He wrote the article last year in Astronomy Magazine about sounds in space. I've been trying to get him to put together a talk based on that cover story. He said he might do it as one of our December shorties. So I'll have him and the lovely Tessa is going to be talking. Tessa?
Yeah.
What's your subject matter?
Recent research in dark energy.
Ooh, that should blow this place apart. Okay, so let's bring him on. Now, Chami, if you want to make your way up here while I'm reading about you, we'll get right down to this. He is a postdoctoral researcher in the UCSB Physics Department, having obtained his Ph.D. from the University of Michigan. Is he? Oh, there he is. You can come over here and stand by me. On second thought, you're too good looking. I hate taller guys. You know, one of my favorite shows is an Indian show that I watch on PBS called Good Karma Hospital. Oh, I cry at that sucker. It was last night. I don't know if you guys ever watched it, but anyway. The underground search for dark matter. That's where it is. Anyway, he got his University of Michigan Ph.D. at Ann Arbor, of all places. He works on dark matter searches now with LZ, which is part of this, and currently taking data. He's also involved with detector upgrades for future searches. And his parents may or may not be watching. Ladies and gentlemen, a big hand for Chami.
Thank you very much for the introduction. All right, let's stick that in there. So thanks everyone for coming and having me at the Santa Barbara Astronomy Unit meeting at the Museum of Natural History. It's a real honor to be here and speak to you all. Thanks for joining me on a Friday night of all nights to learn about science. I'm very excited to tell you about it. So I think I'd like to start with a small video here. So here is what we think galaxies look like and should rotate based on the things that we thought we knew about them, that they're made of stars, dust, and gas, most of which is concentrated in the center of the galaxy. So that's where the gravity is strongest, and that's where it spins the fastest. As you move away from the center, and where most of the mass is, the gravity gets weaker, and the outer stuff spins a little bit more slowly than the inner stuff. So this is what we thought would happen. But when we went out and made the observations, we saw a surprise. It's rotating much faster than we thought. This is a key piece of evidence, and this mismatch between what we expect and what we observe suggests that there's a large amount of unseen mass all throughout this galaxy that causes this rotation speed to be faster. And here's the side by side, so you can see what we expect on the left and what we actually observe on the right. So there's probably excess mass in these galaxies, but if you're not totally convinced by this, that's fair. But anyway, I want to talk about Vera Rubin, one of the astronomers who was pivotal in making this discovery of the galaxy rotations. And she was actually honored this year by having her face on the 25-cent coin. So what she did was she measured the rotation speeds of hundreds of these galaxies and noticed that almost without exception, all of them rotate faster than we expect them to. And here's what she had to say about it. In a spiral galaxy, the ratio of dark to light matter is about a factor of 10. In other words, the stuff that we think makes up the galaxies, the stars, the dust, and the gas, is only a small fraction of the total amount of mass that there is. She went on to say that that's probably a good number for the ratio of our ignorance to knowledge. We're out of the kindergarten, but we're probably only in about the 3rd grade. So when it comes to spiral galaxies, what you see is not always what you get. So you might still be a little bit skeptical, which is fair. And so I want to tell you about one of the most striking visual pieces of evidence that we think points towards the existence of dark matter. So this is an optical image taken by the Hubble Space Telescope. And each of these blobs is an individual galaxy with hundreds and millions of stars. Except for the blobs which have little crosshairs on them. So this one, for example, those are nearby stars. But everything else is an individual galaxy. And the galaxies in these circles, you can kind of see there's more of them within these circles. They're held together by gravity. And this image is peculiar because these two clusters of galaxies have undergone a collision. A kind of peculiar collision because most of these galaxies have passed right through each other. They're kind of too far apart from each other to really interact, so they have mostly gone through each other. But like we've been warned, galaxies can be deceptive. So this is not the full picture. To get the full picture, the Chandra X-ray Observatory has made some observations since this picture was taken. So the pink shows where all of the hot gas in this galaxy cluster is. Hot gas, especially when it gets excited after this collision, emits X-rays, which the Chandra Observatory is sensitive to. So you can kind of see that the hot gas, unlike the individual galaxies, has interacted a fair bit, and it's kind of gotten stuck in the middle. And you can especially see the smaller part, the smaller hot gas, as it's plowed through the larger mass, it's kind of gotten this bow-like shockwave, giving this cluster its name, the bullet cluster. We also know that in these galaxy clusters, the hot gas is heavier, has more mass than the individual galaxies themselves. So in pink, you're also seeing where most of the mass of the galaxy system, of the galaxy cluster system is. It's where the pink is. But this is strange because in blue, which is offset from the pink, you can see where the actual mass distribution is. And this is a measurement of the mass of the system, regardless of what the matter that makes up this mass is. And it's measured using a technique called gravitational lensing, which uses faraway light from behind these galaxy clusters and looking at how much it bends due to the gravity of these clusters. So this technique does not care about whether we can see the mass or not. It is definitely sensitive to where the mass is. So here's another mismatch between expectation and observation. If the galaxy clusters only contain gas and individual galaxies, then we expect most of the mass to be where the pink is. But in fact, we observe that most of the mass is actually not. Now, the individual galaxies themselves that you see, they're not heavy enough to create such a gravitational signature that's seen in the blue. So the conclusion from this is that there's an unseen component of mass in this system that has, just like the individual galaxies, gone through by not interacting and produces the mass distribution you see here. So astronomers, many physicists and astronomers would say that the blue is a tracer of large, gigantic dark matter halos that are shrouding these individual galaxies. Okay. So it's one thing to look in the night sky and observe the motions of these stars and galaxies and infer that there's something invisible there. But a natural question to ask is, well, what is this made of? What particles make up the dark matter? And so, to answer this question, our theoretical physicist friends have taken a lot of, have put in a lot of work and come up with hundreds of models. So in one classification scheme, we see here, arranged by mass, an array of dark matter candidates. So you have ultralight dark matter, you have light dark matter, and just to show who the boss is to the dark matter, they've named it a WIMP. And then you have heavy dark matter, and then realizing that we're not the bosses after all, they've named this particular candidate machos, or massive compact halo objects. If we look at what some reference masses are, these dark matter candidates can range from having the mass of a neutrino, which is the lightest particle that we know of apart from light itself, all the way up to the mass of the sun. So this is probably what Verhoeven was saying, that we're probably still in the 3rd grade. We don't know where to look. But in this spectrum, there are certain areas where it is very theoretically popular to look. And one particular candidate is the WIMP. The WIMP has a mass between a hydrogen atom and a complex protein. And it stands for weakly interacting massive particle. Not very creative, but a very descriptive and precise name to call this thing, because it weakly interacts, as in the case of the galaxy cluster where it just passed through each other, but it also has some mass. So the rest of this talk is going to focus on looking for WIMPs. So what's the idea? How do we do it? Well, our sun, our star, as it goes around the solar system, it goes around the Milky Way with the Earth in tow, it is continuously going through a sea of WIMPs. And because these WIMPs are weakly interacting, they're mostly passing through us without interacting, just like in the galaxy cluster, they mostly pass through each other. So it's really hard to detect them, but these searches are carried out under the hope that what if, however rarely, one of these WIMP particles interacts with the atoms in our world? What would that look like? So that's the next natural question to ask. So how would a WIMP interact with an atom? If it does interact with the regular world, WIMPs are predicted to interact with the nucleus of the atom, the dense core in the center of the atom. And it would come in, it would interact with the nucleus, it would give it a little kick, and then it'll scatter off. So the search strategy would be look for signatures of individual atoms having been kicked from some hypothetical particle. Sounds easy, right? Well, before we get to what such a signature would look like, we have to address the fact that the subatomic world is really, really busy. So, for example, the sun creates a lot of radiation and emits various particles. We get cosmic rays from outer space. We have microwave ovens, we have X-ray machines, cell phones, radio, and you even have natural sources of radiation inside your own bodies. So all of us are exposed to a lot of radiation every day. And radiation definitely interacts with atoms. So we need to have a way to tell apart the radiation from the dark matter signal. Radiation usually interacts with the atoms, with the electrons in the atoms, so it usually kicks out an electron. But we need a way to filter out the signal from the noise. So how do you do a dark matter search? Well, first, since most of this background radiation comes from outer space, from cosmic sources and from the sun, the best way to get to a place where you have extremely low levels of radioactivity is to go underground and to use the Earth as a shield. Then you have to make sure that the experiment that you're building is made of materials that are very pure and very clean and don't have lots of natural levels of radiation, because otherwise you wouldn't be able to see anything in your detector. Finally, it's impossible to eliminate all the sources of radiation. You're still going to have some residual amount left over, and so we have to use every trick that we have up our sleeve to separate these background radiation events from the dark matter signal events. So this is the LUX-ZEPLIN collaboration, or LZ for short. We are one of the few teams in the world that have taken on this challenge of building this very special detector that is sensitive to WIMP dark matter. We're about 250 scientists, engineers, and technical staff from 38 institutions over 4 continents. And this is a picture taken last year at one of our collaboration meetings, where we were all very stressed in this picture because we were pushing towards getting a result out in the following month. So, and this is the smaller team of detector detectives at UCSB, and some of them are here in this room. So we play many roles in this team in the search for dark matter. Both professors here on the top left have led large dark matter collaborations to produce world-leading results, and they've served as spokespersons for those collaborations. We have experts in cryogenics and detector design and detector building who have actually designed and built the very experiments that we're looking at now. We spend a lot of time understanding how our detectors work and the fundamental physics behind these particle collisions and how the signals are produced. We spend a lot of time looking at the data and looking for slight hints of dark matter and extracting that out. We also look for new ways to detect dark matter by exploring new detector technologies, and some of these technologies are led by some of these efforts to find these new technologies are led by some of the youngest people in our team. So that's very cool, and we do basically all of the steps needed in the dark matter search. So where do we do it? I'm going to focus a little bit more on the Black Hills of South Dakota, because this is where the most sensitive dark matter WIMP detector in the world is currently operating. So aside from being geographically striking, it's a forest of green just rising up from the prairie. It also has a lot of cultural significance because this land has a lot of mineral resources, including gold, which led to the Black Hills Gold Rush more than a century ago, and which led to thousands of gold prospectors coming on to see land. And so it has a very rich cultural significance, but it also has a lot of economic and scientific importance as well. The gold found here was one of the richest gold veins that we've seen. I think for more than 100 years, about 10% of the world's supply of gold came out of this land. So to get this gold, they had to dig deep and they had to dig wide. So this is a digital rendering of the network of tunnels and shafts under the surface here. So this is a recent picture. What used to be the Homestay Gold Mine is now called the Sanford Underground Research Facility. And this building here is one of the main entrances down into the mine. So it looks nice here in the summer, but it is South Dakota, and South Dakota gets buried. So this is on my first trip out, and I think a couple of days there we got a bunch of snow, and we were stranded not only on the road, but what turned out to be on an ill-advised hike that we tried to take. But you know, it's just some icing on the cake, right? Like a little bit of snow will help with that radiation shield that we were talking about. So the dark matter experiment, LUX-ZEPLIN, is a mile underground at surf. It's in this cavern shown here in the yellow. This was also the site of a previous experiment. It is the first and most, this old experiment was the first and most significant underground experiment that's been conducted, and that's a story for another day. But the person who led it, Ray Davis, won a Nobel Prize for it. This experiment started in 1917. I think he won the Nobel Prize in 2000 or something out there. But he won the Nobel Prize, and we named the cavern that his experiment took place as the Davis Cavern, and now the modern science is being done inside the Davis Cavern. So yeah, this is him taking a bath a mile underground in the water shielding tank. So the stuff at the mine, you know, because it's a very old mine, the stuff there is old. This is the motor. On the left, you can see the motor that takes us, that lowers us into the mine shaft when we go to work every day. And you probably can't see the date, but on this plaque, the date there is 1933. So they built things hopefully to last back then, because even though we've turned from gold to dark matter now, we still use the same equipment, most of the same equipment. On the right, you can see the elevator doors, if you will. So just to give you a little idea of what the commute a mile underground into the earth looks like, there's this video from Wired. It shows us piling into the cage, as they appropriately call it. I've done this about 100 times now, and that journey is cold, it's wet, it's noisy, and it's claustrophobic. It also lasts about 12 minutes to get down to our level. So this is the 48, 50 foot level. The cage usually makes a few stops on the way down, but it'll pop you out right here, and the Davis Cavern is right around the corner. Unless you're unlucky and this particular shaft is out of order that day, you have to take a shaft that's about half a mile away from the Davis Cavern, in which case you have to trek about half a mile through one of these tunnels underground, or take the subway, which we're taking now. Needless to say, the journey is rough. I mean, you're wet and claustrophobic, and there's dust all over your mine clothes. But once you change out of your mine gear and enter the Davis Cavern, it's like entering a different world. So the environment inside the Davis Cavern is very precisely controlled. It's ultra clean. It's air conditioned. It's well ventilated. It's well lit. It's like really nice to be in there, actually. The only thing is you don't have a lot of natural light. And sometimes when you're working under there, you go down at 5 a.m. and then you come back up at 4:30 and the sun's gone down. So if you're working every day, you don't see the sun for the entire week that you're working. But other than that, it's very nice, and you can see some of the scientists happily working on the experiment here. If you go down the stairs to the left, you'll actually see what the LZ experiment looks like. Or since we closed it up 4 years ago, you'll see what the outside of it looks like. But this is it. This is the dark matter experiment, and this is a large water tank. To look inside, I can split it open like this for you. You can see a person there for scale. It's essentially full of liquid and full of very sensitive light sensors. So on the outermost side, in the water tank, you have this thing is filled with ultra-pure water to shield the experiment from the radiation coming out from the rock underground. And then these little dots are very sensitive light sensors observing the space. It's also observing this green space. This green thing on the diagram here are tanks filled with a special liquid that generates a lot of light when radiation passes through it. So it's kind of like the radiation alarm for the dark matter experiment. But the thing that's actually sensitive to the dark matter interactions is the thing in the center. called the time projection chamber. This is filled with about 7 tons of liquid xenon. It's about a mass of an elephant, I think. And liquid xenon is very cold, obviously. It's about minus 150 Fahrenheit or minus 100 degrees Celsius. So we're going to take a closer look at the TPC next. So here's a nice picture of it. Like I said, it's filled with liquid xenon. Liquid xenon is nice because it's very dense. It's 3 times the density of water. So that means a block of aluminum will float on liquid xenon. And this allows you to pack a lot of atoms of this material into a small space, which is good because you want to maximize the number of atoms you have available for the dark matter to come and hit. It's also low radiation intrinsically. It doesn't have a lot of radioactive isotopes. And it makes it very easy, it's actually easy to purify and clean to the levels that we want it to be. But that's not all. What happens when dark matter interacts in the DPC? Like I mentioned before, we know that the dark matter, the WIMPs interact with the nucleus of the xenon, whereas all the other radiation mostly interacts with the electrons of the xenon atom. But in general, when any particle comes and hits the liquid xenon, it creates a flash of light. So it hits the liquid xenon goes and hits other atoms of xenon, and each of these struck atoms produce a little flash of light. This is immediately detected by these arrays of light sensors on the top and bottom. But not only light, the xenon also frees up some charge, some electrons. And this charge is extracted out of the liquid and also measured. So when something comes and hits our detector, we essentially get 2 signals, the light signal and the charge signal. So like I said, liquid xenon has a lot of nice properties, but probably the best property that it has is that based on the amount of light and charge that is produced, it can tell apart the signals that are created by the WIMPs and the signals that are created by the background radiation. So this is a plot that we typically look at. This is a figure from one of our scientific papers, where on the horizontal axis is basically the amount of light produced, and the vertical axis is the amount of charge produced. And you can see most of the data points that we have occupy this top region. That's where the background radiation band is. And due to the special property of liquid xenon, the area where we expect the WIMP dark matter is down here. So you get a very clean separation of your background from your signal, which makes this a great material to do a dark matter search with. So I want to show you or have you listen to what our data sounds like. So our data is recorded by these light sensors. We have about 500 of them in the TPC and several hundred of them in the outer detector that is basically the radiation alarm. So one of our collaborators created a sonic representation of our data as it comes into our detector in real time. So the key to this is that the piano sounds you hear will be scatters in the TPC. That's what you want to hear, want to listen for, because the dark matter comes and scatters in the TPC. That's what it's sensitive to. In a synth sound are all the signals that the outer detector records. So the radiation alarm, basically. And because radiation tends to scatter multiple times, for example, it can scatter in the TPC and then immediately scatter in the outer detector, any sounds you hear where the piano and synth are occurring at the same time, you can exclude that from your analysis, because that, we know, cannot be dark matter, because dark matter will only interact once in the TPC. So, and the pitch of the sound is the energy of the scatter. So I'm going to try and play this for you, hope you can hear it. quietest, the most radio quietest of places that we can construct, we're constantly being bombarded by radiation. And some of them are true scatters in the TPC, or just the piano sound, but you can see quite a lot of them have also coincident scatter in the outer detector as well. Now, because of the, flip back to the last slide, because of the separation that we get from the radiation and the WIMP signal, you'd expect a WIMP to sound different than any of those sounds that we just played. Maybe it sounds like an electric guitar or something. But the point is we can listen for that sound very, very precisely. So we did. We've been listening for since 2021, and we haven't heard it yet. So, so in the absence of a positive signal, what we can do is set a bound on how strongly it can interact. Because if it interacts rather strongly, we would have been able to see it in the detector. And so we can say, well, dark matter that interacts this strongly does not exist, because we would have seen it. So we set a new record for this kind of thing in the search for dark matter. This is an article from last year. So new results from the world's most sensitive dark matter detector put the best ever limits on particles called WIMPs, a leading candidate for what makes up our universe's invisible mass. One thing to note is that finding out what isn't true is just as important as finding out what is. So given this null result from our experiment, we should re-examine our theories and re-examine our models, refine our search strategies, and kind of narrow down the dreams that this stuff is supposedly made of. So I think, in my opinion, it's still a very significant result. So I'm getting close to the end here, so I want to end with two stories that are analogous to how the story of dark matter might play out. And to do this, we have to go back a couple of hundred years, when astronomers noticed that the journey of Uranus around the sun seems a bit quick, like it moves quick in some areas of its orbit, and it moves slow in some other areas of its orbit. And they thought that this erratic behavior could be explained by another planet yet undiscovered outside the orbit of Uranus that's like kind of tugging on Uranus, making it go fast and slow. And so this astronomer calculated exactly where he thought Neptune, well, this undiscovered planet should be, and he sent this letter to the observatory, and the very same day the observatory pointed their telescope at the sky, and the very same day, the day that they got the letter, they discovered Neptune. So this is a very striking example of, people call this astronomer the guy who discovered the planet at the point of his pen. So a very strong prediction led to a very strong discovery. So this was in 1846, and it was a good year for astronomy, obviously, but it's a bad year if you're making a map of the solar system, because as soon as you put it out, it's immediately out of date, because the last planet out here is Uranus, so they didn't put Neptune in there yet. But if you zoom in a little bit, you'll see a strange thing. Inside the orbit of Mercury, there's an orbit labeled Vulcan here. Now this was also a hypothesized planet. So this map was doubly wrong, actually, but okay. So the reason that Vulcan was hypothesized was that Mercury's motion is also anomalous. Specifically, the point at which it closest approaches the sun tends to rotate, and astronomers observed that it rotated a bit faster than it should have, according to Newton's laws. So they tried, they said, well, obviously the same guy actually who did Neptune's like, well, there should be another planet in here in Mercury. But no one ever found it. Vulcan does not exist, right? The explanation for the precession of Mercury's perihelion had to wait until the very foundations of physics had to be changed by this guy called Albert Einstein with his theory of general relativity. So he writes in a letter in 1915, perihelion motions explained quantitatively, you will be astonished. So this required a new theory which closely linked mass and the curvature of space-time, and predicted that Mercury being close to the very the massive sun, it should affect its orbit in a non-Newtonian way. So you can probably see where I'm trying to go with this. You had two objects in anomalous motion. One is Uranus, and that led to the discovery of something new, Neptune. But the other one, Mercury, there wasn't a new object that was discovered. In fact, it was a new law of physics that had to come about to explain this. So I think we could be at a similar crossroads with dark matter. We see that galaxies and stars move in weird ways, and we think that there's something out there, but we don't know for sure. So the search will continue. So LZ will continue to take data until 2028, looking for WIMPs. And I think I'll hope to be invited back to tell you about it. So thank you very much for listening. This axis shows you how much light you observe in the detector that is detected promptly. And the vertical axis is how much charge that the detector produced. So the radiation stuff produces more charge than you would expect a WIMP to produce. That's the main distinguishing factor between the two. Yeah.
How did you establish that WIMPs interact with the nucleus of atoms? If the atom is what you
Yeah.
Can you repeat the question?
Yeah. How do we know that WIMPs interact with the nucleus and not with the rest of the atom? If we haven't discovered the WIMP yet, how do we know that? So we know that WIMPs are electrically neutral, because if they were not, then it wouldn't pass through each other like in a galaxy cluster. So, and because it's a neutral particle, it can kind of move through the electron cloud of the atom without interacting, and we assume that there's some sort of interaction in the nucleus. But you're right that we don't know that for sure. Yeah.
Do we know for a scientific fact that dark matter actually exists, or is it still a theory?
So the question is, does dark matter actually? We don't know for a scientific fact that a particular dark matter candidate exists. We know from observational evidence that we know from a wide range of observational evidence that something like dark matter should exist that affects the universe gravitationally, but we haven't been able to pinpoint exactly what particle it is yet. There is controversy, of course, like some people think that there is no dark matter, but instead modification of the laws of gravity can explain all of this. So there's an ongoing, sometimes heated discussion about these two various things. Yeah.
Are there other similar experiments for different masses of dark matter? Like for instance the machos, or is there other people looking for those?
Yeah. So the search for dark matter here is the so-called direct search, where we look for the direct interactions of dark matter with our regular atoms. The searches for other types of dark matter, like machos, are sometimes called indirect searches, because they look for indirect signatures of stuff moving under the influence of machos, for example. Yeah.
Exactly who funds all this research?
Pardon?
Exactly who funds all this research?
Actually, we have a list of the funding agencies here. So most of the effort in the U.S. is funded by the Department of Energy, and we get other funding sources from our international collaborators, like some of them here, the Swiss National Foundation. We get some money from the state of South Dakota, and very expensive. Yeah.
You're going down a mile deep to the cavern
Yeah.
to minimize the radiation
Yes.
effect. How is the observance happen if you're down so deep? What allows you to study the possibility of dark matter if you're preventing the
Yeah. So how are we sensitive to dark matter deep underground? Because presumably the Earth is a shield. So the Earth is a shield for radiation coming from outer space, that's for sure. But WIMPs are so weakly interacting that they could pass through, the current estimates are like millions of light years of lead without even interacting once. That's how weakly interacting they are. So the WIMPs go through the Earth no problem, but it stops everything else.
so if they were not weak, they would get blocked.
Yes. Yeah.
So you've been able to put some bound on how weakly interacting they are. Is there like a level at which you could get this bound where we could say, okay, WIMPs are not a thing. Like it's low enough, now we can stop.
Yeah. That's a complicated question because when we say that we've excluded dark matter interacting at a certain strength, we make that statement under certain assumptions of what the WIMPs, what the exact WIMP hypothesis is. So there are models that theoretical physicists come up with and say, well, if WIMPs were a thing, here is the region where we'd expect them. Like you'd kind of think of like a treasure map. And it's the job of the experimentalist to kind of systematically cut out pieces of that treasure map and exclude them. But it is possible that the theorists have not considered everything. So the little island that they point to us may not be the only possibility where dark matter exists. So it is possible that we'll keep searching and searching and searching, but the interaction of dark matter with regular matter is arbitrarily weak that we would not be able to find it. Yeah.
So, in the future, what kind of industry would benefit from this knowledge? You
Yeah.
mentioned that the Department of Energy is one of the big benefactors.
Yeah.
How would this be used, in the future?
That's a good question. Yeah, so the question was, how would this dark matter search be of any, maybe a practical value in the future? So the goal of building our experiments is rather abstract because we're searching for a dark matter hypothetical thing that we may not be able to find, but the tools that we invent to search for it can be used to push the boundaries in various other aspects, like for instance medical physics, where xenon detectors can be used to do medical imaging. It can be used for to monitor nuclear explosions, because these detectors are very sensitive. If you can install them in certain sites where you suspect there has been a nuclear explosion from a rogue country doing nuclear tests, for example. And another application is, in the process of doing this, we come up with a lot of new techniques, like computational techniques and data and analysis techniques that have broad applications. Yeah.
So do you have any theories that can explain what we observe without invoking dark matter?
Could you repeat the question?
Do you have any theories? You mentioned earlier that some people say dark matter doesn't exist and actually need to expand their theories.
Yeah.
Are there any theories that can explain what we observe and that don't need dark matter?
Right. Are there any theories that can explain the gravitational effects that we see, but that are not dark matter? Yeah, there are. I'm not an expert on them, but they mostly have to do with changing how gravity works. So, for example, to explain the rotation of the Milky Way, why it rotates fast outside, there's a theory that modifies the law of gravity such that for very low accelerations when you're far out, you're more likely to rotate faster. So that's a direct modification, and the problem is that, in my understanding, which is limited, generalizing those types of theories to fit everything is difficult. So, so there's a challenge there, and the evidence for dark matter, I've shown you the dynamic evidence, 2 pieces of evidence, but there's many more. There's pieces of evidence that come from right after the Big Bang, so billions of years ago, where we see the initial seeds of the dark matter collapsing, and we see it in like the light that we observe from billions of years ago today. So these theories that modify gravity have a harder time explaining those other pieces of evidence, but they do exist. Yeah, Thomas.
Going back to your imagery, you had the blue and pink blobs.
Yeah.
The blue was farther out in the collision than the pink. Is there a reason you'd expect the dark matter to, I guess, exit the collision faster than just the regular matter that's contained in the blue?
Yeah, so the question is, why is the blue kind of pass through more easily than the pink has? Yeah, so the pink is showing the locations of hot gas in the galaxy cluster, which are emitting X-rays. So this hot gas definitely interacted with each other through electromagnetism or something like that. So they encounter a lot of friction and they get stuck in the middle. Whereas the individual galaxies are too far apart to directly influence each other. So they've gone through, and also the dark matter is too weakly interacting. So they've also gone through. Yeah, I think there's a question back there.
Yeah, you're trying to prove that Neptune exists, and there's people out there who are trying to prove that Vulcan doesn't. Is there a sense of competition, like who's going to finish the race first? Because it feels like those two things might be in direct contrast with each other.
Are you specifically referring to Neptune and Vulcan, or?
No, I'm using the same
Yes.
example you were using, which is you're trying to prove that dark matter exists, and there's people out there who are trying to prove that there's a theory out there that doesn't involve that dark matter. Is there a sort of competition there, or are you kind of just working independently? Well,
to be honest, my read of it is that the two camps aren't talking to each other enough. So the gravity people are doing their own thing and saying, well, this is totally explainable by gravity. And the dark matter people are like, oh, this is totally dark matter and we're going to find it. But there isn't a lot of fruitful conversation between those two camps, in my opinion.
Why do you think that is?
I don't know, it's an interesting fact of the sociology of the field, I think. Like when you start to believe something, you want to continue going on with it. But there's a couple of examples of people who started out in the dark matter camp, but then they've noticed certain things that don't quite click, and they naturally see that the gravity thing makes more sense, and so they've like moved the bulk of their research to the other side. So there's interesting cases like this, but it's I think at the end of the day not a scientific question currently, which is unfortunate. Yeah. Why couldn't it be both? Yeah, that's totally possible. In my opinion, there's some arguments why the gravity thing isn't so viable, but this is just my opinion. And the reason is that Einstein's theory of gravity is complete and like self-consistent. And when you try to change it, it like breaks that self-consistency. So it becomes a less beautiful and less consistent theory. So that's one argument why people are reluctant to consider the alternative.
Do you know, are there any models, or do the models of dark matter include angular momentum? And is there evidence of angular momentum in dark matter?
Yeah, so I can take that question in two ways, like angular momentum in terms of the spinning of the galaxies.
Something, yeah.
Yeah, right, so there is, when people model how the dark matter actually lives in these galaxies and galaxy clusters, they have to consider it that it spins a little bit. And so that's how it's called. You're rotationally supporting it all being together because of its spinning. There's another way I can take your question, and the actual particles of dark matter could have a property called spin and angular momentum, and that's the quantum property of these particles. And that is, there's tons of theories talking about dark matter particles with spin and without spin. But for example, in LZ, we look for both spin-dependent interactions between dark matter and xenon nuclei, and also spin-dependent interactions with.
I was kind of thinking about how regular matter collapses and forms a rotating body like a galaxy.
Right.
Is that going to happen with dark matter as well?
No, dark matter usually forms more spherical structures because it doesn't interact with itself. It doesn't kind of form a disk like a galaxy would. So dark matter halos are more spherical in shape. Yeah.
I have a question to follow up on that one. You mentioned that that there's a difference between like the detecting WIMPs that have spin and WIMPs that don't. What differences, like how do you what differences in measurement do you apply?
Yeah, it's a good question. The measurement is the same because all we're looking for is something to show up in. I think I went past it. I'm sorry. Did I? I'm looking for that plot. Oh yeah. All we're looking for is something to show up in this region. So after the fact, we interpret it as a spin-independent or a spin-dependent coupling.
And then one more question. I was wondering, you mentioned that there were for other masses of weakly interacting particles, you look for like indirect things. Do we ever do that for WIMPs? Like, do we ever look for, like, instead of directly observing them, do we ever say, well?
Yeah, I think so. So one good place to look for them is the centers of galaxies, where you'd expect the dark matter density to be the greatest. So you'd expect in the center of galaxies to be most likely where WIMPs or other dark matter candidates could collide with each other and produce regular matter. So we have telescopes out looking at the centers of galaxies and looking for anomalous signatures of things coming out.
And one more thing. Can you back up? When you said that when dark matter collides, it produces regular matter, how do you do that?
It could. It's a hypothesis. Yeah.
Yeah, we have another question? I'd like to hear it. You have a question, Gary? I can't formulate my question. Years ago, I read an article that was trying to look at the different candidates for dark matter particles, trying to determine particles with particle length or wavelength.
Yeah.
And I forgot the details of that. But they decided that it was more wavelength and then eliminated one of the usual candidates. If you remember that, was that eliminated or not?
Oh, so WIMPs are definitely particle-like candidates. You can have stuff that's lighter than WIMPs that are wave-like. I'm not sure what the specific article you're referring to is, but lately, because our experiments have been too good at not discovering WIMPs, people have been shifting focus to other lighter dark matter candidates, so and are coming up with new experiments to look for wave-like particles.
That's why I did volunteer the question.
There's a question back there.
Oh yeah. Now that you've what are the plans to update the experiment? Is it more xenon? Is it deeper mines?
Yeah, great question. So we have there are three main experiments like ours that are currently operating, one in Italy and another one in China. Right now, it's in a weird, flirty negotiation stage between our experiment and the Italian one to kind of merge and make a super xenon detector. So we'll put together our xenon and have a bigger target. There's also ideas to what kind of upgrades we can do to the existing technology. So one thing we're working in UCSB in our lab is dissolving hydrogen in the liquid xenon to look for lighter dark matter. because xenon, while it's a great target, it's not very good for looking for light dark matter, because you can kind of imagine the light dark matter being a ping pong ball, and the xenon is this big heavy bowling ball. It strikes it and it doesn't rock the xenon much. So if you put in something lighter like hydrogen, that momentum is more effectively transferred, and the hydrogen then can go make the signal in the liquid xenon. So there's tons of ideas that we're in the process of throwing around and trying to find the best one for what comes next.
And so far, you have made any of these light sensors light up inside that xenon tank?
Not from dark matter.
So you can recognize some radiation that
Yes.
you know isn't a WIMP.
Oh, we understand the radiation of our detector very well. Yeah.
So you're getting lots of those.
Yeah.
Got a question more?
Over here.
Okay, yell it out.
If the preponderance of dark matter is in the center of galaxies, is there any interaction with the supermassive black hole?
Does the dark matter interact with the supermassive black hole? I think it does. I'm not sure how it differs from the interactions between regular matter and supermassive black holes. I think a dark matter particle falling into a black hole will undergo the same process of like loss of information that any other particle would. I mean, regular matter tends to arrange itself in interesting structures around black holes, like these accretion disks and structures like this. I don't think dark matter will do that, but it'll still fall in.
You said that it doesn't interact with itself,
Yeah.
but it interacts with other matter, or no? It only interacts gravitationally.
So far, we think that it only interacts gravitationally. All these other things, its self-interactions and interactions with regular matter are a possibility, but it's not been discovered yet.
I mean, does it gravitationally attract with itself?
Yes. Yeah. Yeah.
President Jerry again.
I found the article.
The axion, right? Yeah, it's the other popular candidate for dark matter. That's a whole other story, but yeah, it's much lighter, and there's also dedicated experiments that are really coming to the fore now, in dedicated searches for it.
Tell me more about this xenon. Is it in the air we breathe?
Yeah.
Is it rare?
It's rare. I forget the exact percentage, but the xenon that we use in our detectors is actually extracted from the air as a byproduct of, I think, like steel making, where you extract out the oxygen first, and then so xenon's a byproduct. It's expensive because there's so little of it, and you have to do a lot of processing to get it very pure.
Is it bad for us, like radon?
It's an anesthetic. Xenon is not radioactive, so it doesn't hurt us in the way that radon does. But I think if you breathe it, your voice becomes very deep. So like the opposite of breathing in helium. And I think it knocks you out if you breathe it enough. Yeah.
I'll get your question next. Aren't they doing deep stuff in Antarctica? Looking for what, guys?
Neutrinos, yeah.
Have they found any of those?
Yeah, they found plenty of neutrinos there.
You haven't found one with...
No.
I was a West in high school. There are four-word acronym for nerd. Nearly, never mind. Go ahead, sir.
Yeah. Does the world of dark matter researchers, do they interact with the world of the dark energy researchers and vice versa?
Yeah, they do.
Okay, I mean, theories going back and forth and explanations?
Yeah. But it's one of those things where we understand neither of the things very well. But, I mean, I'm definitely not an expert, but there are people who, especially people who do cosmology, who study both dark matter and dark energy, because they're, right now, the two primary driving forces on how our universe evolves.
And after hours, they sit in the bar and they say, we don't know.
Sorry?
And after hours, you sit in the bar and you say, we don't know either.
Yeah, exactly. Yeah.
This is all under the assumption that dark matter is dense and that there's other theories, like it could be the other forms of dark matter there. I think there's a theory.
Sorry, could you speak up a little bit?
I think this is all under the assumptions that these are WIMPs and not the other forms of dark matter that you proposed there, or there's like another theory. I think I've heard primordial black holes as one of them.
Right.
Why did you choose specifically WIMPs to look?
Yeah. So the question is, why did we focus on WIMPs instead of the other dark matter candidates? The story of WIMPs is interesting, and that's why it used to be the most popular. Well, it still is, I think, but now there's the axions have come into the picture. But they're very popular because WIMP particles with WIMP-like properties, including the rarity of interactions with regular matter, such particles are predicted in very different areas of physics, predicted by people who are trying to solve very different types of problems. So the common solution of a WIMP-like particle coming from very different and unconnected parts of physics is something known in the field as the WIMP miracle. The WIMP miracle. It's a very attractive candidate to look for, because if dark matter really is the WIMP, then everything will fall into place like very naturally. But sometimes that's not the best metric to go off of.
You know what's amazing to me is these evolving paradoxes. What goes around comes around. You get told initially in astronomy, light can't even leave a black hole. It's all gone forever. Now Hawking comes along and we got radiation from it. Now you're telling me, or they're saying, whoops, dark matter cannot react or act with regular matter, and yet you're trying to?
Yeah.
And you think you can. There'll be one little area where we touch.
Yeah, we don't know that they don't actually react.
You don't know that.
We don't know. We don't know if it reacts. Yeah.
I sometimes look at air. I can't see air either, but I know it's here. What's the difference?
Yeah. I mean, it's a big question because we have these like incredible pieces of evidence from galaxies and stars and whatnot, and it's just so annoying sometimes that we just can't find it in the lab. But that we might just have to live with that eventually.
Dr. Chami Amarasinghe, everybody. What's a good time? You're looking at any particular moment that you will discover these things, or shall we give you a year maybe? All right. Well, I would like to present you before we leave with our official SBAU classic ceramic cup. These things sell for big money at Sotheby's, Electro. And I would advise you not to have your first cup of coffee in it because your honorarium check is or something. Raise your hand if you're one of Amarasinghe's, Chami's guests. Are you here? Just the lady, okay.
Yeah, the little ones all.
The little ones, the fat, did they enjoy themselves?
They love.
Okay.
Except for the baby, yeah.
All right, well, we're going to socialize now. Come get your goodies, and we'll see you next month for UFOs. Thank you.